Today's lesson is looking at electrolytic cells. Up till now we have been talking about cells and we've commented on whether or not things would be spontaneous. Today we get into those ones that are not spontaneous. So electrolytic cells are ones where they require an external power source in order to go, because they're not going on their own. So if we look at that galvanic cell, that's where it spontaneously goes and produces electricity. So in the galvanic cell is like our batteries, but the electrolytic cell is like when we recharge our batteries, because we have an external power source and we make the reaction go exactly backwards. So if you look at the equations on these two examples, right, on the galvanic cell, the iron is becoming iron plus 2, so it is being oxidized, and the copper 2 is becoming copper, so it's being reduced. Whereas in the electrolytic cell, exactly the opposite is happening. The iron is going from the ions to the metal, so it's being reduced, and the copper is going from the metal to the ions, so it's being oxidized. The cell potentials, if we look at them, remember we always flip the one that's the oxidation reaction, and when we flip that, the cell potential, we flip the signs, and so when we do that calculation, for the galvanic cell we get positive 0.78, for the electrolytic cell we get negative 0.78. So same value, but opposite signs. Because with the electrolytic cell, that's the minimum voltage that has to be supplied in order to make the reaction happen. So these are reverse of each other, and if we think about what's going on there, we can kind of compare the two. So the voltaic or the galvanic cell, we have our reactants becoming our products, plus they give off some electrical energy. In the electrolytic cell, we have the opposite reactants becoming our products, but they require electrical energy. Voltaic is going to be spontaneous, electrolytic is not. Delta E, or that voltage, for the voltaic cell is positive, and for the electrolytic cell is negative. So we have some interesting applications of electrolysis, such as recharging batteries, which we've already mentioned, refining metals from their ores. So there's lots of metals that use electrolysis, and they use a lot of electricity when they're refining metals. It's a very high amp situation for these ones. Cathodic protection to prevent corrosion. So you might have heard of things where they do run a current through to prevent corrosion. Electroplating, so lots of things are electroplated. I gave a few examples here. Basically anything where they want to kind of make it cheaper by having the interior be a less expensive metal, and then they coat it with a prettier or more expensive metal on the outside. So whether that's chrome on a bumper, or our dollar coin is electroplated. Many fixtures, jewelry, decorations, various things can be electroplated. In the example at the side there, we have a iron spoon or a steel spoon being plated with silver. So with these applications, we do sometimes want to do some calculations, such as, well, how long do we have to run a current through? What current do we need? How much metal will we get when we run a current through? So we have some cell stoichiometry on these, but we're always on these ones focused on really just one half of what's going on. We really want to know about that metal being produced in these questions. Not always metals, because electrolysis could involve some other things being produced, but with these stoichiometry questions, they're a little unusual in that instead of writing our balanced net equation, we're often writing a balanced half reaction. So, and we don't really concern ourselves with the other half reaction to do the calculation. Same as our usual steps of stoichiometry though, write our balanced equation, convert to moles, convert moles to whatever units we need, and use the mole ratio, and then convert to whatever units we need. So with these, we have some formulas that we're going to look at, but they can also be done using dimensional analysis should we choose to. So the other really big important piece of information we need here is what's happening with that current. And this involves a few calculations we haven't looked at before. So charge is equal to current times time, and Q stands for quantity of charge here, not quantity of heat. And remember, I is for intensity of current, so Q equals IT means the charge equals current times time. And molar charge of electrons, we're given in coulombs here per mole. So this is a constant that is in your data booklet on the miscellaneous page. And it is known as Faraday Constant after an early chemist / physicist. The distinction is a little unclear when we're talking about these topics that are covered in both subjects. So with that number, right, it's just calculated that is the value of the charge on a mole of electrons. So when we combine those two things together, we get that the moles of electrons is equal to current times time divided by Faraday's constants. So if we look at those units, current is measured in amps or coulombs per second. So we have coulombs per second times seconds if we put our time in seconds. So it's important that we always take our time and move it to seconds. Even if it's hours, we've got to move all the way back down to seconds. So our first example here, if we look at what we have, what mass of aluminum is produced. So our half reaction that we're concerned with is the aluminum. Now, is that the only thing going on here? No. If we run a current through molten aluminum chloride, one electrode is going to be giving us aluminum. The other electrode is actually going to be giving us chlorine. So we know that that's going on. We're not concerned with it for our calculation. So in terms of our given information, current and time are the two things we can use to figure out our electrons. So that's why I put them below the electrons here. We're looking for mass of aluminum. So using our formula, moles of electron equals current times time divided by Faraday's constant. We know all of those pieces of information. Now you'll notice I took the current that's in amps and I specifically showed the amps as being coulombs per second, but remember that's the same thing. The reason I did that though is it allows us to see we have seconds on the bottom, which are going to cancel seconds on top, leaving us with coulombs on the top. So then we have coulombs divided by coulombs per mole. So when we flip that coulombs per mole, we again have coulombs canceling, just like our seconds canceled, but we're left with moles on top. So we get moles of electron. So that's our first calculation step in terms of find moles of our known. Once we found moles of our known, we need to convert to our other substance, so use our mole ratio, and then convert to the units we're looking for, so in this case mass, so we're going to use the molar mass. Some people like to do this as one big giant calculation because you can take this first calculation and just put these last two fractions right on the end of it to calculate straight to mass of aluminum, but then don't say it's equal to moles of electrons because it would not be. So second question, we're looking for volume of chlorine. So a piece of information you may have forgotten, but it is in your data booklet, is the molar volume of any gas at STP is 22.4 liters. So we're going to need that piece of information in order to get to volume of a gas. So our half reaction that we're concerned about there, let me get the color being the same as what we usually use. So we've got chlorine ions, chloride ions I should say, going to chlorine plus 2 electrons. So again, we've got current and time. That's enough information to find our moles of electrons. Once we have our moles of electrons, we can do our ratio between electrons and the substance we want, in this case chlorine gas. And then our last step, we're not going to mass. We're going to use this fact about gases at STP and figure out the liters of chlorine. So feel free to pause, take a moment, do the calculation, and we get that it's 16.7 liters of chlorine. So those two were both going the same direction, where we knew current and time, and we were trying to figure out how much of something was produced. The next example, we know how much we want to have produced. We're looking at how, so we could look at either current or time in one of these questions. In this particular question, we're looking at time. And very often on these questions, we end up with some pretty large time amounts, right? This one up here, our time was an hour, and it only produced 3.36 grams. So you can see this one's 2 hours, and it's producing 16.7 liters. So we're not getting huge amounts produced in a fairly long time when we're talking these kind of currents. So these are kind of slow reactions at these low currents. If we want it to be a fast reaction, we're going to have a much, much, much higher current, which is typically what happens in the industrial processes. You've got a much higher current. So with these ones, I kind of glossed over this. We were converting that time into seconds. So remember, 60 minutes in an hour, 60 hours in a second, so 3,600 seconds in an hour. That's where we're getting this calculation from. So going the other direction, when we're looking for time, we're kind of going to expect that we end up with some pretty large numbers, because this is going to be time in seconds. So here we have enough information about the chromium to find moles, because we can look up our molar mass and figure out our moles of chromium. From there, we can do our mole ratio to find our electrons. And then we can rearrange that formula, Ne equals IT over F. Well, we want to know T. So multiply by F, divide by I to get time alone. And again, those steps, we could be looking at our dimensional analysis. Right, so we're at moles of electron. Faraday's constant is coulombs per mole, so that would cancel out our moles, leave us with coulombs. And current is coulombs per second, so if we flip that upside down, we end up dividing by current, and we get our units in seconds. So as I mentioned, we end up often with these ones some pretty high numbers, 5,206 seconds. So we want to convert that back into minutes. So divide by 60 will give us minutes, which is 87 minutes. Question says answer to the nearest minute. So either one of these two ways of expressing 87 minutes would be answering to the nearest minute. So 87 minutes or 1 hour and 27 minutes means the same thing. As I mentioned, we could do this same kind of calculation, fully dimensional analysis. So here's what it would look like if we went dimensional analysis all the way across. And that's our last topic in redox chemistry.